Okay, so let's chit. Okay, so let's chit chat about the lab. It's been a little bit of a crazy morning already. Okay, so you should have two graphs. Your position time graph is going to look something like this. Okay, all right, going up to 3 meters. Okay, so what if all you see is this graph? If all I give you is just this graph, you should be able to discern a lot of information from that. So first thing that you should notice that, oh, this object changes direction because there's a relative maximum, or you can draw a tangent line that has a slope of 0, or you can say the slope changes from positive to negative. Okay, so that's the first thing we can figure out. We can also figure out that on the way back, on the way down, it's going to be not as fast because that slope on the return trip is more shallow than the trip going up. So I got to figure it's going to change direction, and when it changes direction, when it's going back, it's not going to be going as fast. Okay? So I can figure all of that out just by looking at this. Okay? And it'll start with positive velocity, it's going to go to 0, and then it's going to end up with a negative velocity. So here's the most critical thing. So Carson, on your group, okay, we're going to use your group as an example. When you get to that box where it says used for the calculation that elapsed time, when it got to 3 meters, what was your group's time at that point?
2.99.
2.99. So let's just call it 3 seconds. Okay? So if I'm in Carson's group, this is going to be 2.99. We'll just call it 3 seconds. Okay? So whatever you have at the end of that second interval, when you add those two times together, that is the most critical time that you need out of all of this data, okay? Because that's going to tell you when the velocity goes to 0. So the first thing I'm going to do when I look at Carson's graph, then I'm going to have this velocity time graph, okay? I'm going to go to 2.99 seconds on this graph, and that's when her velocity time graph has to go through 0, okay? So whatever you have as the end of that, at the end of that second interval, this is the most critical thing. That's when the velocity on your velocity time graph crosses that 0 meters per second mark. Okay? So take that point and transpose that down. Now, here's the problem with this velocity time graph. For 12 years in your high school or education system at Mays or wherever you've been, on graphs you've always been told to play connect the dots. Okay, so here's what you want to do. You want to sit here and go, oh, at the end of the first interval you had a certain positive velocity. At the end of that second interval you have another velocity, and then over here you have some negative velocity, and then at some other time over here you have another negative velocity. And what you're tempted to do is connect the dots and go from here to here, and then take this point way out like this, and then have something like that. Okay, because that's what you all have been taught to do. Connect the dots. It's a vital skill, don't get me wrong. We can't do that here, and here's the reason why. Let's say, for example, Jake was timing that interval from 1.5 meters till when it hit the wall. Okay? When Jake stops his stopwatch, the final velocity of that cart at that point is 0. So even though we talk about a velocity during that interval, at the end of that interval, that velocity is actually 0. Okay? So this is why, if I'm Carson, I'm going to come back here and go, okay, that's 2.99 seconds. Because at the end of that interval, that was my velocity. Okay? At the end of 2.99 seconds, I wasn't moving. The velocity was 0. So if I'm Carson, I got 2.99 seconds. So down below here, I need to figure out when the plunger hit and when the plunger released. So I'm going to go back here to 2.89 seconds. I'm going to subtract 1/10 of a second and come back here to 2.89. And then I'm going to move forward a tenth of a second and go to 3.09. So here's what I've got. So here's my 2.99 second mark. A tenth of a second before it stopped, that's when the plunger hit the wall. A tenth of a second afterwards is when the plunger had left the wall and it's rolling backwards. So come in here and draw a line like this, okay? So at this point, okay, Carson's going to have what were your two positive velocities going in?
1.01.
1 point what?
Per second, 1.01.
1.01 and
Then 0.50.
0.50? Okay. So these are going to be her velocities coming in here like this. So slowing down, then it's going to hit the wall, then at this point right here, this is when it's going to hit the wall. Okay, that's what's going to be critical. Then once it hits the wall, this is when that plunger is being compressed. So from here to here, what's happening is that it's slowing it down. That's we're storing potential energy. At that point, it stopped. Now, Mother Nature at that point doesn't like potential energy. Mother Nature likes kinetic energy. So then that spring is going to expand. Now the problem is you're going, well, I don't know what that velocity is when it takes off. You're right, you don't. Okay? Sometimes we have imprecise data. Sometimes we just kind of have to guess some numbers. But Carson's going to know a couple of negative velocities over here. So what she can do is take these lines and make them meet. So you're going to end up with something that looks like this. But here's the most critical. This is the first thing I'm going to look at. Okay? I'm going to find the sum of that at that second interval. That's when that velocity time graph has to cross through zero. And then come back a tenth of a second. That's when it hits. Go forward a tenth of a second. That's when it leaves. So down here, right here, there's 12 things that you need to have on this graph. Okay? So the first thing is when it hits the wall, when the spring is compressing, when the spring is expanding, and when the plunger hits the wall. Make sure on your graph, and I'll get you started. That point where that line begins to drop rapidly, that's when the plunger hit the wall. Okay? So think of the sequence. Like imagine you could watch it in slow motion. Oh, you'd see it hit, and then you'd see it compress, and then you'd see it expand, and then you'd see it leave the wall. Okay? So that's the first thing that you need, because you really can't answer the questions on the back until you get this thing done. Then indicate when the car is slowing down or speeding up using arrows. Oh, here it's slowing down. So put a down arrow. It's slowing down. When it hits the cart, when the plunger hits, oh, it's slowing down. Okay. Then this is the region when it's speeding up, because that's when that plunger is expanding and it's pushing it back, and then it begins to slow down again. So basically, you're slowing down almost the entire trip except for when that plunger is expanding. Okay? Then, label the sign of the velocity and the acceleration in each segment. Let me redraw this a little bit cleaner. Here's what I don't want to see. Okay, so here's your graph. Don't come out here and put, oh, positive, negative. I have no idea what positive, negative means. I don't know if you're talking about velocity. I don't know if you're talking about acceleration. So in each, you're going to have 4 distinct segments. 1, 2, 3, 4. In each one of those segments, you clearly indicate, oh, I have either like, you put positive velocity, positive acceleration, negative acceleration. Do not just put plus or minus and think, I'm going to know what that means. Okay, I'm not. All right? So you clearly state, hey, this is what we've got going. Do not just put plus or minus. You tell me, is it positive velocity? Is it negative velocity? Is it positive acceleration? Is it negative acceleration? Okay? Now, when you get to answering these questions on the back, okay, Be very specific when you're answering these. So for example, if you just say, well, when the plunger hits the wall, okay? There's a whole bunch of things that what happens when that plunger hits the wall. Are you talking about when the plunger is compressing? Are you talking about when the plunger is expanding? Okay? Are you talking about when it's rolling towards the wall? Are you talking about when it's rolling away from the wall? Okay? So be very specific when you're answering those questions. Now, when you get to questions 8 and 10, okay, what I would recommend, unless you really want to get picky with doing triangles and rectangles and it's a god-awful amount of work, what I would do, let's say your graph looks something like this, which hopefully it does, okay? What I would recommend, just to make the math easy, here's your velocity time graph. Come over here and like split this top line and do like an average. So use this as the height of this rectangle. So kind of split the difference in this horizontal, in the sloping line here. You're going to lose some area here, but you'll basically pick it up over here. So kind of come in here and go, okay, hey, this is kind of my velocity across like that. And then come down here like this, and now you have kind of a rectangle, okay? And then do the same thing over here, okay? So do something like this. So now on this one, you're going to have some negative velocity across like this. So leave, kind of split the difference. So this is going to be some negative velocity. Now on the time, on this one, only use the time from here to here. Don't use the entire time, okay? Only use this from here to the end. So hopefully what you should see, hopefully, is that you get something close to 0 when you add those two values up, okay? If you get something way, way off, like if you're getting 4, you have done something horribly wrong, okay? Now, here's the other thing. This is a fairly complex lab. When I look at 8 and 9, when I tell you to show your work, let me tell you what does not constitute showing your work. 1.1 times 2 equals 2.2 does not constitute showing your work. You have randomly written down numbers that have no meaning whatsoever, okay? I don't know what they are. I don't know what 1.1 is. I don't know what 2 is. I certainly don't know what 2.2 is, okay? And then, oh, a miracle happens and I'll put meters on the end. You have to show the work. This is about conveying information. This is not about getting an answer that goes on the right. Show your work. Show the units that go with it, okay? Now, when you get to this question about F equals MA, all right? So here's the cart. We're going to spend a lot of time talking about F equals MA, okay? So here's a couple of ways you can view this. You start off with some big positive velocity, okay? So when that leaves your hand, you have some big positive velocity. So when that cart is rolling towards the wall, one of 3 things can happen. There is no friction, and the velocity vectors just stay the same because Mother Nature is lazy prima donna and Mother Nature doesn't want to change things, okay? And the cart maintains the exact same velocity as it rolls, so that's option number 1. There's just no change in the velocity. Option number 2, it's going to slow down. So if you consider this being V1, then as it rolls, V2 is a little bit smaller, V3 is even smaller. So if you're slowing down, then your acceleration vectors point in the opposite direction. So anytime something slows down, your acceleration vectors point in the opposite direction of your velocity vectors. Okay? So if I take my remote control and I give it a push, oh, it comes to a stop. Because my velocity vectors are in this direction and my acceleration vectors are in the opposite direction. The other thing I want you to get out of your mind is that acceleration is negative, and every time acceleration is negative, you slow down. No, 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 no. You can speed up with negative acceleration. Okay? Don't think that friction is always negative. Okay? Friction can be positive. The only thing true about friction is that it always acts in the opposite direction of motion. So if I push my remote control in this direction, friction goes in this way. If I push the remote control this way, friction goes in this way. So friction always acts in the opposite direction of motion. Friction is never going to make you speed up, which would be really weird. Okay? Because like, oh, I need to stop my car, I'm going to hit my brakes. Okay? Be really weird is like you have to decide, oh, I'm going to hit the brakes. Man, is friction going to make me speed up or slow down when I hit my brakes? Okay? That would take driving to a whole new level. It's like, what happened? I hit the brakes. Oh, officer, I'm sorry, but friction made me speed up. Really? Oh, insurance rates would skyrocket. Okay? But we're not have to worry about it. You know friction is always going to make you slow down. Okay? It's always going to happen. Now, let's talk about that big sign in the back, F equals ma. Is mass ever going to be a negative number? No, it's a scalar quantity. Okay, I'm not going to say, what's the mass? -5 kilograms. What? No. Okay, so mass is always a positive number because it's a scalar quantity. So, that's a positive number. So if I have negative acceleration, what sign does my friction have to have? Or does the sign of my force have to have? Negative. Okay? So friction or force and acceleration always have to have the same sign because mass is always a positive number. Okay? Any questions? Anything at all you say, oh, maybe a little sketchy on this answer? This is the time to ask. Going once. Going twice. Nathan. Should have said it faster. You're wearing flannel, so I'll let it go.
Okay. How? So calculating the whatchamacallit, the
Okay, you've
displacement.
got to get more specific than whatchamacallit.
On question 8 and 10,
Yeah,
calculating the displacement
which is the area.
area.
Yeah.
So you just, I don't know, because when I found the difference between it for number 11, I got a probably too high number. That's not.
What did you get?
I got -0.36 meters.
That's okay. I can live with it.
All right.
You kind of had sketchy data, so that's okay. Now, if you had gotten, a difference of 3.6, okay, legitimate concern. But the main thing is, here's the kicker. Could you give your paper to Jack, and could Jack see exactly how you did your calculations?
I think so. You ought to.
Okay? Well, so we came up with this in my third block class yesterday. When in doubt, ask yourself, in terms of showing work, WWBD. What would Burkamp do? So we thought about having bracelets that we can sell them as a fundraiser for the solar project. So when in doubt, ask yourself, WWBD. Is this the kind of work that Burkamp would show? And if you say no, don't hand it in. Okay? All right. So are we good, Nathan?
Yeah, we're good.
Okay. Anything else? Going once, going twice, solar. So get that hand in. Now, I beg of you, make sure that you have gone through this list and you have done everything that is on here. Okay? Speeding up, slowing down, acceleration, velocity, hits, compresses, leaves, all that stuff. Okay. Yes, ma'am.
Okay, I'm just gonna warn you. I don't even know what I did. I don't know what I'm doing. I don't know
Okay.
anything about any of it.
Can you come in during?
It doesn't conflict with like photos, I think, like club photos.
Okay. So you got some good starts. You just need to tweak some things. Okay. So like let's just get started. The initial position is zero. So this is where this graph needs to start. This is your position time graph. No. This is your position time. Your position time graph needs to start at 0 and go up to.
I don't even know what I did when I
Okay. Yeah, so your position time graph just should look like this, right? So even if you look at the scale, you're going 0.5, right? So if you're gonna let this be 0.5, then you can't start skipping it and then go by 1. So what I would do, this doesn't have to be that precise, I just go 0, 1, 2, 3, okay? And then when you get done, it's just gonna look like this. So just go 0, 1, 1, 2, and then you're gonna go to 2.99 seconds. And again, see how, this is why,
Didn't it go all the way, it was on that right here.
well, okay, then that's fine. Then like skip 4 and go 1. And then skip 4 and go 2, and skip 4 and go 3, because you need to end up way out here at 8.42 seconds. So you need to end up, you know, way out here. So go like 1, 2, 3, 4, 5, 6, 7, 8. Okay, so maybe like skip to 1, 2, 3, 4. Okay? So start with that. Both of these, do that. Let's go. 1, 2, 3, 4, 5, 6, 7. Okay? Start with that. Okay? All right. Okay.
What do you mean? It's more like water and already. How much was it?
Okay. So here's how this week is going to play out. So today and tomorrow we're going to deal with vectors. So today we're going to deal with what we call the graphical addition of vectors using the tip-to-tail method, which sounds very complicated, but it's really not. You all know how to do it. I just have to convince you that you know how to do it. So today is going to be all the graphical stuff. So this is why hopefully you have a protractor and ruler, because you're going to need that. So then tomorrow we're going to do this with trig functions. Okay? Same idea, we're just going to use trig functions. Just sine, cosine, tangent. Nothing weird like arctangent or cosecant squared or trig identities, anything like that. Okay? Or the unit circle. Nothing like that. Then on Friday we'll review. Monday is the test for the velocity unit. Okay? Now, so when you talk about this process with vectors, okay? First off, just look at the word vector. Okay, hey, we're going to use vectors. So Jake, because it's a vector quantity, what does it involve?
Displacement, not displacement, direction and magnitude.
Fantastic, direction and magnitude, okay? So the only thing we're going to use this for is vector quantities, okay? We're not going to use it for scalar quantities because scalar quantities are just numbers. We don't have directions that go with them. So there's a couple of rules that we need to establish. The first rule that we need to establish is that when we're going to draw this out using angles, here's this x and y axis, okay? So rule number 1 is that the positive x-axis is defined as 0 degrees, okay? So when I say something's at 0 degrees, that's only existing on the positive x-axis. 0 degrees is not up, it's not left, it's not down. 0 degrees is the positive x-axis, okay? The other rule is that any angle is going to be measured around counterclockwise from that 0 degrees. So for example, if I say, oh, we're at a 45-degree angle, 45 degrees is going to go from here up to 45. If I'm over here, this might be 120 degrees. If I'm down here in this fourth quadrant, okay, if you remember your quadrants from math class, first quadrant, second quadrant, third quadrant, fourth quadrant. So if I'm down here in the fourth quadrant, that might be like 350 degrees. So angles are never negative. Okay, you are never going to have negative angles. Never, ever, ever are you going to have negative angles. All the angles are going to be measured around like this from this positive x-axis. Okay, rule number 1. Okay. So the magnitude is going to be determined by the length. Is it 5 centimeters? Is it 7 newtons? Is it 5 meters per second squared? Whatever that vector quantity is. And then the angle is going to tell us which direction it's going to point. Okay, got that. Cool. All right. So how you use this tip-to-tail method. The big idea of the tip-to-tail method is that you're trying to figure out what's the net effect of these vectors that are acting together. So let me give you a simple example. So let's say that we're going to have a tug of war, okay? So Force Bailey, is going to be pulling with 20 newtons at 0 degrees, okay? So right away, I have satisfied the idea that this is a vector quantity. I've given the magnitude, which is 20 newtons, and I've given my angle at 0 degrees. So right now, this is a vector quantity. Now, if I just said Bailey is pulling at 20 newtons, that's not a vector quantity, because I don't know which direction that she's pulling. Great, she's pulling at 20 newtons. Good for you, okay? I don't know which direction she's going. Doesn't make, I don't know. She's pulling for 20 newtons. It's going to be left, right, up, down. I don't know, okay? But as soon as I put at 20 degrees, then it becomes a vector quantity, okay? Now, Connor is going to be pulling this way. So force Connor is going to be 15 newtons at 180 degrees. Okay, and again, this is a vector quantity. Tug of war. Bailey's pulling this way with 20 newtons. Connor's pulling this way at 15. Now, who's going to win? Bailey or Connor? Bailey, by how much? That's a 20.
5 minutes.
By 5 newtons. In which direction?
0 meters.
5 newtons. Bailey's going to win by 5 newtons at 0 degrees. Okay? Everybody cool with that? You all just did the vector addition of vectors using the tip-to-tail method. And you go, no, we didn't. Brookcamp, I said, yeah, you did. Here, and you did. So let me explain how you know this. So when you deal with vectors, there's 2 types of drawings that we're going to do. And we're going to do a lot of these. When you draw it like this is what's called a free body diagram. Okay? Free body diagram. Usually it's FBD. So what you do on a free body diagram is that you treat the object, whatever that is, a box, a squirrel, a rocket, whatever it is. You treat it as a single point, and then you draw all the vectors, whether it's velocity, whether it's acceleration, momentum, force, doesn't make any difference, okay? You draw all of those vectors acting out from a center, okay? So if I draw it like this is not the tip-to-tail method. This is the free body diagram. What it does, and we're going to draw a lot of these, okay, is it shows all of the vectors acting from a common center, okay? So this just gives me the big picture. Okay, hey, Bailey's pulling this way, Connor's pulling this way, okay? This is not tip-to-tail. All I'm doing is saying, somebody could look at this and go, okay, this is what we got going. Now, to do the tip-to-tail method, you pick one of the vectors. We'll do Bailey's first, okay? So, and you are actually going to draw this out. This is why you're going to use a ruler, okay? So you're going to draw out, maybe in this case, I'm going to let 1 Newton equal a centimeter, okay? So I would actually draw that out to a designated length, okay? This isn't just a sketch. I'm actually going to draw this out. So I'm going to come out here and I'm going to draw force Bailey, which is 20 newtons at 0 degrees, okay? I'm going to draw that first vector, okay? Boom. Now, this is why we call it the tip-to-tail method. So from the end of this vector, now I'm going to draw Connor's vector, okay? So Connor's vector is 15 newtons at 180 degrees. So from the end of this, I'm going to come back here like this, and I'm going to go, okay, here's force Connor.
Pardon the interruption. Teachers, would you please release orchestra members at this time to get ready for pictures? Could you please release orchestra students at this time for pictures?
Okay. So now I've drawn Connor's. Okay? If it was 10 newtons, I'd draw it 10 newtons long. If it was 5, I'd draw it 5. If he was also poling in the same direction of 0 degrees, I'd draw it out that way. Okay? So the end of Bailey's vector, okay, is like a whole new x and y system. This just becomes the end. I'm going to draw Connor's vector from the end of that, and it's going to point backwards because that's the direction that he's pulling. If he was helping Bailey out, I draw it in the same direction. If he was pushing at a 90-degree angle, I draw it at a 90 degree, whatever that is. Okay? So all this does is that it establishes a new point where you're going to draw the new vector. Okay? The other way you can kind of visualize this is that imagine that I could cut, after I draw this, imagine that I could cut this out and drag it and put it here. Okay? And I'm going to take that vector, I'm going to put it right there on the end. That's the other way that you can visualize it. Okay? Now, what you are ultimately after is what's known as the resultant. Okay? So the resultant is the net effect. Okay? Of what's going to take place. So here's the story. If you've ever been to Australia, you see a lot of kangaroos. Don't ever hit them at night when you drive. They make a god-awful mess of your car. Okay? So it's sort of like hitting deer in Kansas. If you're driving on the outback of Australia, you have to be wary of kangaroos. Okay? Because unfortunately, kangaroos, when they get startled, number one, they're nocturnal. And then they get startled, they jump up. And so then you're hitting them in your windshield, bad things happen. So when you draw your resultant, you want to think of a roo. Okay? Good on you, mate. That's a kangaroo. It's a ripper. All right. So let me explain what roo stands for. Rho stands for the resultant goes from the origin out. Okay? So resultant, origin, out. Okay? Now let me explain what that means. So if I come up here and I go to where I started, okay, I go back to that initial point where I started drawing Bailey's vector. And I'm going to draw that resultant from where I started out to where I end up. Okay? So in this situation, my resultant is going to tell me, oh, this is 5 newtons, okay, at 0 degrees. So the net effect of Bailey pulling with 20 newtons, Connor pulling back in the opposite direction of 15. The net effect of that is 5 newtons at 0 degrees. Okay? Now, this is why you draw your resultant from the origin out. Because if I draw the vector from where Connor's vector ended up back to the origin, then that would be pointing in the opposite direction, and that would be 5 newtons at 180 degrees. Okay? That's why you always have to go back to the origin and draw that outward. Okay? It's a kangaroo. It's a ripper. Ripper. Going from the origin out. Good on you, mate. Now, that one's relatively simple. But here's another way that you can think about this. Here's another option. Australia, they have this term where you go on a walkabout. Okay? Literally, you just go out in the bush, you need to find yourself, you go out and just go on a walkabout. It's a legitimate thing. So let's say you go on a walkabout. So imagine that you're going to start here and you're going to walk 20 steps in this direction. Okay? So Fisher is here or Nathan's here. Nathan's here. He's going to walk this way 20 steps. Okay? Then he's going to turn around and he's going to walk back 15 steps. Now, at this point, he realizes, oh, I don't have my calculator. Hector, being his friend, goes, hey, I'll hook you up. I'll get you your calculator. So what this tells us is which direction Hector has to walk to get to Nathan to give him his calculator. So Nathan walked out 20 steps. He turned around and he walked back 15 steps. Hector is going, hey, I got to get him his calculator. So Hector is going to walk 5 steps at 0 degrees to get to where Nathan is. Okay, so that's the other way that you can think about this, just in terms of how you walk. Okay, got the idea? That's what I said. You all know this. I just have to convince you that you know it. Now I'm going to change it up a little bit. Okay. So now we'll have a soccer ball. Okay. So Devin's going to kick the ball this way. Force Devin. 20 newtons at 0 degrees. Okay? So he's going to kick the ball this way. Okay? At the same time, Adana is going to kick the ball with a force of 15 newtons at 90 degrees. Okay? So imagine that here's a soccer ball. Devin's kicking the ball this way, Adana's kicking the ball that way. Now, before you do anything, okay, Jaden, where is the ball going to go, roughly? Is it going to go between them? Is it going to go to the left? Is it going to go down? Where's it going to go? Upward like this? Up and to the right? Is it going to be closer to Devin's or closer to Adana's?
Devin
Why?
is more newtons.
Yeah, there's more force, right? So here's the story. What's going to happen, and this is going to be important. I know that that ball is going to go something like this, okay? Less than a 45-degree angle, because Devin is kicking with more force than Adana is, okay? So I know when I give this angle, it's going to be less than 45 degrees. Now, again, this is not tip-to-tail method. This is just a free body diagram. All we're showing is that Devin's kicking the ball this way, Adana's kicking the ball that way, but I can conclude from that that ball is going to go somewhere in between. Okay? Got that. Now, we're going to do the tip-to-tail method again. We'll draw Devin's first. So here's force Devin. Okay? 20 newtons at 0 degrees. Now, from the end of this, I'm going to take Adana's vector here, and I'm going to draw that from the end of Devin's. Okay? So now I'm going to take that, cut it, drag it, I'm going to put it there. So this is going to be force Adana, 15 newtons at 90 degrees. Now I'm going to do the Australian thing. All right, good on you, mate. Where are we going to draw our vector? From the origin out. Okay, so here's our horribly drawn kangaroo. Okay, imagine that's a kangaroo. So the kangaroo is going to go from the origin out. So what you are going to do initially, you're going to draw this out. You're going to draw this vector with a ruler. You're going to take a ruler. You're going to draw this out. Boom. Then you're going to take this, and you're going to draw this like this, and then you're going to draw that vector. Okay? Then you're going to take a ruler, and then you're going to measure this length. Okay? So you're going to get this. You're going to measure this length. Then this is where you have to have your protractor. Then, hold on. I'm going to go grab my protractor. Hold on. Give me 1 second. My protractor's in the bottom. And I got the big protractor. Okay, so then, here's 0 degrees. So I'm going to center this. Okay? So here's 0 degrees. I'm going to come up here, and I'm going to measure this angle. So this would be like at about 28 degrees. So I'm going to measure this length. I'm just going to make up a number. Let's say that that's 24 newtons at 28 degrees. Okay? So now, notice with these two, don't take 20 and add it to 15 and go, oh, that's 35. It's not it. It's like you're measuring the hypotenuse of that triangle. Okay? So you are physically going to measure that length, and then you're going to take your protractor, and then you're going to measure that angle. So again, if you like the walking analogy, Angel starts here. Angel's going to walk 20 steps in this direction. He's going to stop. He's going to walk up here. At this point, he is stopped right here. Okay? Jake says, "Ah, man, Angel, I got to get you your water bottle." Okay? How am I going to do that? So I have to tell Jake how to get to Angel so that Angel can get his water bottle. Oh, Jake, here's what you have to do. Jake, you need to walk at an angle of 28 degrees, and you need to take 24 steps, and you'll get to there. So there's two ways that I could get to this point in space. I could walk out. I could do the Angel path. I could walk here, stop, turn, and get to this point. It's valid. Or I could start here, walk 24 steps at an angle of 28 degrees, and still end up at the same point. Okay? So this is the resultant. Here's the two individual vectors. See the pattern. Getting them. Now, here's as complicated as it gets. Okay? So go back to the soccer analogy. All right? So here's the soccer ball. So Alexis is going to kick the ball with the force of 20 newtons at an angle of 40 degrees. And then at the same time, Jake is going to kick the ball with a force of 15 newtons at 120 degrees. Okay? So, here's the soccer ball. Lex is kicking the ball this way, Jake's kicking the ball this way. Okay? Got that. Which direction is the ball going to go? What does the angle have to be between? 40 and 120. Closer to 40, closer to 120. Closer to 40, why? Yeah, it's a bigger number, right? Because Alexis is kicking the ball with more force than Jake is. So when I get done, I know that vector has to go somewhere in between. Okay? Cool with this. So, that just tells me a big idea of what's going to happen. Again, this is the free body diagram. That is not the tip to tail method. That's just my free body diagram. So, here's what's going to happen. You're going to start, you're going to draw an X and Y system. Okay? First thing that you're going to do is you're going to draw Alexis's force first. So, what you're going to do, you're going to take your protractor like this. You're going to measure up 40 degrees, make your mark, boom, draw that line. Okay? That's what you're going to do. This is why you have to have a protractor and ruler. So you're going to draw this system, take your protractor, center it here, come up to 40 degrees, draw that line however long that is. So I'm going to come in here, doink. So there's my vector. So that's 20 newtons at 40 degrees. Here's my first vector. Okay? Now, when I draw the next vector, which is going to be 120 degrees. So this right here is a whole new X and Y coordinate system. So imagine that you are drawing this vector and this is a new X and Y coordinate system. All this vector does is get you to the end of the vector. Okay? When you measure 120 degrees, don't put your protractor like this and measure around 120. Treat that as like a new X and Y system, okay? So I've got this, like this. I want to measure around 120 degrees. I'm going to make a mark. Whoa, nope, hold on, come back. There we go. And then, once I get that mark, then I'm going to draw that line just like that, okay? This way you have to have protractor. All right, so imagine that we did that, and we're going to go something like this. So there's force Jake, 15 newtons at 120 degrees. Okay, so here's my two vectors. I drew Alexa's. From the end of that, I took Jake's, plopped it right down there. Okay, that's what I've got. Now, I'm going to draw my result. So that resulted, I'm going to go back to where I started. Back to home base. I'm going to go back to where I started. And I'm going to draw that line from here out to this point. Okay? I'm going to go from here out. So, I'm going to draw that line. I'll make it a different color so we can see it. So there's my result, and that's what I'm after. Now, again, you are going to take this and you are going to measure that length, okay? You're going to measure however long that line is. That's going to get you your magnitude. Don't measure this line, don't measure this line. You're from here measuring out to there. So let's say that's, I'm just going to make up a number, that's 17 newtons, okay? Could be centimeters, it could be meters per second squared, as long as it's a vector quantity. Now, the tricky part is the angle, okay? When you measure that angle has to be measured back from this initial positive x-axis right here, okay? So you've got to go from here, and you're going to measure around like this. This has nothing to do with it. When you're measuring that angle, you're going to start right here, and you're going to measure counterclockwise. So in this one, I had like 71 degrees. So I'd say 17 newtons at 71 degrees, okay? Whatever that is. And again, here's the idea. Devin starts here, and he walks 20 steps. He stops, he turns, he walks another 15. He goes, oh man, hypothetically, oh, you found your calculator?
Yeah.
Okay, so let's say Devin was in earlier trying to find his calculator. So let's say Devin has lost his calculator, okay? He's going, man, I'm out here, I don't have my calculator. Carson, the good friend that she is, she goes, oh, Devin, I got your back, okay? I've got your calculator. So what this is telling Carson to do, this is telling Carson she needs to start here, and she needs to take 17 steps at 71 degrees to end up where Devin is. Okay? Got the idea. Okay, so stop that camera for a second.
Age members, please report to the auditorium for pictures.
Okay, so here's what you're going to do. It's going to be the easiest 5 points you are ever going to get in this class. So all of these vectors are going to be based upon these, A, B, C, D, and E. So you can either work off of notebook paper. If you want to work off of graph paper is kind of cool because it always gives you like a visual X and Y system. So the first thing that you're going to do is you're just going to draw these vectors so that you have an idea of what you're dealing with. So literally, the first thing that you're going to do is you're going to take your ruler and you are going to draw a vector 5 centimeters long, okay, at 0 degrees, and we're going to call that vector A. Now, when you are drawing these, when you measure out that 5 centimeters, so here's your protractor, you're going to measure out that length of 5, okay? When you put that arrowhead on the end, and you have to put an arrowhead because it shows you the direction. So when you draw that line to be 5 centimeters, don't put the arrowhead on the end of it and make it even longer. So make a line 5 centimeters long and then put the arrowhead here so that it doesn't extend past the 5 centimeters. So then you're going to draw vector B, 3 centimeters at 90. If you want to draw these separately, that's cool. If you want to draw them from the same common center and go, oh, here's vector A, vector B, 3 centimeters at 90 degrees, okay? And then you got C, which is at 120, which is going to be somewhere, I don't care. You can either draw them separately or you can draw them all from the same common center. I don't care. That's up to you. Personal preference decision. It's the easiest 5 points you will ever get in this class, okay? Now, when you get down to number 2, so now we're going to begin to add these vectors together. So the number 2 is as easy as it gets. We're just going to add vector A to vector A. So on number 2, here's what you're going to do. You're going to draw vector A. Okay? Sit. Just draw vector A. 5 centimeters. Boom. Sit. Sit. Now from the end of vector A, I'm going to add vector A to itself. So from the end of this, I'm going to add another vector A to it. Okay? So it, vector A plus vector A. That's what I've got. Now, I'm going to draw my resultant. Resultant goes from the origin out. So I'm going to come here and I'm going to draw another line that goes all the way out to that end. So my resultant here is going to be 10 centimeters at 0 degrees. Okay? Now, I don't want you to look at this and go, oh, all we always have to do is just add the numbers together. No, 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 no. We added the numbers here because they're both going in the same direction. Okay? So, on what I want to see on another sheet of paper, do not try and draw this here. You're going to put these on a completely separate sheet of paper. And on the back side of this, I show you, here are the steps to follow. Okay? So on the back side of this, if you don't know what to do, you just work through this example. And I gave you a complicated example because if you can figure out the complicated example, the other ones are going to be pretty simple. And literally, you follow these steps every time. So on another sheet of paper, you're going to draw vector A, draw the resultant. So what I want written here is the value of the resultant. So right there where it says A plus A, what I want, you've got A plus A. So what you're going to write is 10 centimeters at 0 degrees. So there's going to be 2 bits of information I should find for every one of these numbers. I should be able to clearly see the diagram and keep them numbered on another sheet of paper. Here's number 2, here's number 3, here's number 4, okay? Draw them out separately, okay? Keep them separate, okay? And then you're going to measure that resultant, and then you're going to write that down here. Now, let's talk about number 3. So on number 3, here's what I'm going to get you started on some of these. On number 3, you're going to add vector A to vector B. So I'm going to draw vector A. Here's my 5 centimeters. And then I'm going to draw vector B from the end of that. And then I'm going to draw that result. Okay? So you're going to take your ruler, measure out 5, make a 90-degree angle, come up, draw that. Now, I need this angle. So I'm going to take my protractor, set that back here. I'm going to measure this angle right here, which in this case is at like 24 degrees. And then I'm going to measure that length from here to here. So when you get done with number 3, this is roughly what this thing is going to look like. You're going to measure this angle, you're going to measure this length. There's the value of the result. Adana walked here, she turned, she walked here. She forgot her pale blue water bottle. Devin, being the nice guy that he says, he's paying it forward. Hey, Carson brought me my calculator. I'm going to take Adana her nice pale blue water bottle. So this is going to tell Devin how to walk to get Adana her pale blue water bottle. Okay? Got that one. Now, that one with B plus D. This one's a little bit tough. Okay? So on number 4, so I'm going to give you a sketch so you know how this thing is going to look. So here's my X and Y axis. Vector B, 3 centimeters at 90 degrees. So I'm going to start here, I'm going to come up, and I'm going to draw vector B. 3 centimeters at 90 degrees, boom, straight up. Now, D is 6 centimeters at 250, okay? So to get to 250, you're here. This is a new X and Y system. So 180 gets me to here. So if I take that 250 minus 180, I get 70 degrees. So what I'm going to do is I'm going to realize I get 180 to here. Then I'm going to put this like this. And then I'm going to measure another 70 degrees to get down here. So I'm going to start here. There's 0. There's 180. Another 70. That gets me to 250. So I'm going to draw this vector down here like this. Okay? So there's vector D. Now, Tyler started here. Okay? He's here. He's going to walk up here. He's going to turn. He's going to walk down right here. He's left his nice black notebook. Okay, he needs it. Adana says, hey, I'm going to help you out. Okay, I got my pale blue water bottle. I'm hydrated. I can help you out. So we've got to tell Adana how to walk to get to Tyler. So that resultant is going to start here. It's going to come out here like this. Now, the angle gets tricky. This angle here has to be from this positive x-axis. So I'm going to start right here at 0. So I'm going to measure around like this. So there's 180. And then I'm going to measure this angle right in here, which in this case is like 46 degrees. So this little bit of angle in there is 46 degrees. So I'm going to take, to get this whole thing, I'm going to take 180 plus 46 to get into that angle. So Tyler walked here, he stopped, he turned, he came down here. Adana says, oh, I'm hydrated. I've got my cool blue water bottle. I must get Tyler his notebook. So this is telling Adana, because she's going to start where Tyler did, and she's going to walk out here like this. So she's going to walk at, say, I don't know, 226 degrees, okay? And this is going to tell her how long she's going to walk. So when you get done with number 4, this is what this should look like. This is just a crude sketch, but that's what it's going to look like when you get done. Okay, I'm done. You're on your own. If you want to work on notebook paper, you can do that. If you need graph paper, there's a stack of graph paper on the back. If you don't have a protractor and ruler, I do have some that you can borrow, but get your own. Okay, there we go. That was exhausting.